Today, I'm going to discuss the application of residues to evaluate real integrals. So far in the class, we have evaluated integrals of three types. First type is integral from 0 to 2 pi when the integrand is a function of sine theta and cos theta only. And in that case, if you remember, we have taken the contour of integration to be a circle with center at 0 and radius 1, and we make the substitution z is equal to e iota theta e iota theta, and then using this substitution and Cauchy's residue formulae we evaluated the integral, and we also evaluated integral of second kind when the limits of integration are from minus infinity to infinity and the integrand is a rational function. Say integrand is of the type small fx over capital Fx, and in that case we have considered the case when the denominator function, that is fx, capital Fx, has no zeros on the real axis. For example, we have considered these kind of integrals. First integral, in the first example, I have chosen the integrand to be the function x square over x square plus a square, x square plus b square. You can see that here the denominator, that is x square plus a square, x square plus b square, has only complex zeros. That is, if you evaluate the zeros of this term, they comes out to be x is equal to plus minus a iota and x is equal to plus minus b iota. So they are completely imaginary. So in the next example also, if you evaluate the zeros of the denominator, that is x raised to power 4 plus 1, its zeros comes to be complex numbers and they are not real zeros. So in these types of integral, we evaluated the integral using Cauchy's residues theorem, and for that we considered the contour as a semicircle of radius capital R, where this capital R is very very large, and in the calculations we take this R approaches infinity and we break the integral minus infinity to infinity into the integral from minus R to R and then plus integral CR in the upper half plane, and then we evaluate the integral. And in the same way, we can use the method described in solving the integrals of type 2a to solve integrals where the integrand involves a function fx with multiplication a cos ax or sin ax. And in, for example, if we want to solve integral 0 to infinity cos ax over x square plus 1 dx, then for this particular kind of integral, we first check whether the denominator term has real zeros or no real zero. So if we check x square plus 1 is equal to 0, then x comes out to be plus minus iota, which is completely imaginary. So we have seen that this type of integral also falls into the category 2a. So we use the same method, but first we convert this integral into easier form. That is, we since there is cos ax involved in the integrand, so we evaluate integral 0 to infinity e iota ax over x square plus 1 dx, and in the end we take the real part of this integral because cos ax is real part of e iota. We have also discussed Jordan lemma in the class, and the statement of Jordan lemma is given in the notes. You can read from there. So with the help of this Jordan lemma, we can make our calculation more easier. So we use this lemma in the calculations. So now, next type of integral which I want to discuss with you, and which is next topic of our lecture, is that integrals of the type from minus infinity to infinity, where integrand is again a rational function fx over capital Fx, and the main thing is that in this type of integral we consider those rational functions for which the denominator has zeros on the real axis. That is, the capital Fx has real zeros. The zeros of capital Fx lies on the real axis. They are not complex. They are not completely imaginary. They are completely real, and hence they lies on the real axis. And for this type of integrals, we use another method that is almost similar to the above method, but there are certain things which we need to consider for this special type of integral. Now, since this rational functions in this rational function, the denominator term has zeros on the real axis, so for the zeros of capital Fx which lie in the upper half plane but not on real axis, we make semicircle C capital R of radius R centered at 0, and for zeros of Fx lying on real axis, we make semicircles C small ri of radius small ri respectively around each real zero of capital Fx. So the method is almost same. Here the denominator term involves real zeros also, and for those real zeros we make small semicircles around those real zeros, and we name them by CRIs. Now at the end we take capital R approaches infinity and small ri's approaches 0 to solve the integrals using Cauchy residue theorem. So I will try to explain the method using this example. So example on page number 3, that apply Cauchy's residue theorem to evaluate integral 0 to infinity sine pi x over x1 minus x square dx. Now first step, whenever you see the rational functions which does not involve any theta, then you check the rational function, you check the denominator terms. Now when you check the denominator function and calculate its zeros, you see that its zeros are x is equal to 0 and 1 minus x square is equal to 0. Now x is equal to 0 and 1 minus x square is equal to 0 implies the values of x are 0 and plus minus 1, which are completely real, and they lie on the real axis, and it has no other 0. So the poles of the rational functions are 0, 1 and minus 1. So we consider the integral e I pi z over z 1 minus z square dz along the contour C. And why we have considered this integral? Because we know that sine pi x is the imaginary part of e iota pi x. So at the end we will get the integral 0 to infinity e iota pi x x1 minus x squared, and then we take its imaginary part, and that will be the answer to our problem. So the main important thing here is the how to consider a contour C that will make the contour C free of any pole. So for that we consider the contour C consisting of, first of all, one real axis from minus capital R to minus 1 minus small r1. Then a semicircle CR1 with small radius R1 and center at minus 1. Then we consider real axis from minus 1 plus R1 to minus R2. Then a semicircle CR2 centered at 0 and radius R2. R2 to 1 minus R3. Then we consider a semicircle CR3 with center at 1 and radius small r3. Then our contour also consists of real axis from 1 plus r3 to capital R, followed by a semicircle C capital R with center at 0 and radius capital R very large. Combining these 8 parts, we get the contour C, which has no poles of fz, that is free from the poles of the integrand. So our requirements of Cauchy residue theorems with the help of Cauchy's theorem, we can evaluate integral fz dz over C, and the answer comes out to be 0 because the function fz now has no pole inside this contour C. So function fz is analytic within C. And because it is analytic, therefore by Cauchy's theorem this integral is 0. And in the next we also evaluate this integral by parts. That is, we join the parts, we separate the parts of the parts 1 from 8 of the contour C and evaluate these parts separately, and then we evaluate the integral from 0 to infinity e iota pi x x1 minus x square dx. So if we separate the contour C into the 8 parts, then in the right hand side of 1 we get that this integral breaks into integral from minus r to minus 1 minus small r1 plus integral over the semicircle CR1 plus integral from minus 1 plus r1 to minus r2 plus integral over the semicircle C small r2 plus integral from r2 to 1 minus r3 plus integral over the semicircle C with radius small r3 plus integral 1 plus small r3 to r plus integral over the semicircle circular arc CR where R is large. So we have completed the contour and now we solve the integrals in the right hand side of one separately. So first we consider the integrals consisting of real axis only. So we consider integral from minus R, capital R to minus 1 minus R1 plus integral from minus 1 plus R1 minus R2. Note, I am not considering the semicircular part, that is integral over CR, C small r1. I have not considering this while I considering the integrals over real axis only. So I am not considering the circular part integrals. So next, the real axis part will be integral from r2 to 1 minus small r3. Again, we will not consider the integral along this circular arc CR3. So we move forward and go to integral 1 plus small r3 to capital R. Now you can see that real axis parts are complete here. So because we have taken this r1, r2, r3 very small, so we will take that this r1, r2, r3 approaches 0 in these integrals. Now if we approach them 0, that is if we take the limit that small r1, r2, r3 approaches 0, and you can see that because we are integrating along the real axis, and on the real axis we take z is equal to x because there is no imaginary part. The points are on the real axis. So we substitute z is equal to x and we get that integrand becomes fx dx, and when we take r1 approaches 0, the first term goes, first integral will convert, and we take capital R approaches infinity, we get that the first integral becomes integral from minus infinity to minus 1. The second integral become integral from minus 1 to 0 because r1 approaches 0 and r2 approaches 0. Third integral becomes integral from 0 to 1 because r2 approaches 0, r3 approaches 0. And the fourth integral from 1 plus r3 to r will be converted into integral 1 to infinity because r3 approaches 0 and capital R approaches infinity. So, and when you see, we can combine this these integrals with the help of integral calculus, that these integrals becomes integral from minus infinity to infinity fx dx, and we name this part of the integrals to be 3. And please check that I have mentioned in the notes that integral fz dz over c is equal to 0 to be 2. So now we will evaluate integral along the circular arcs. That is, we will evaluate integral over c small r1, integral over c small r2, integral over c small r3 and integral over c capital R. If we evaluate this and combining with 3, we get that all the right hand side integrals will get covered. So, first of all, we consider integral of fz dz along c small r1. Now, please notice that this c small r1 is a semicircle and we have taken the orientation of this semicircle clockwise. You can see in the picture in the notes. So this CR1 is a semicircle clockwise in the clockwise direction in the upper half plane, and the center of this CR1 small is -1 and the radius of this semicircle is R1, which we have taken to be very small. That is, at the end we will take this R1 approaches 0. So, equation of the circle with center at -1 and radius R1 is given by mod z plus 1 is equal to R1. And if we open this mod, we can see that the points on the semicircular arc will be of the form z plus 1 is equal to r1 e iota theta. So z will be of the form -1 plus r e iota theta, and therefore dz will become iota r e iota theta d theta. But this substitution holds only for integral over CR1 because CR1 is a circle with center -1 and radius small r1. So if we substitute these things in our integral, we get that integral e iota pi z dz over z 1 minus z square over CR1 is converted to integral from pi to 0. Why it is pi to 0? Because we are taking integral clockwise. So theta will move from pi to 0. And then substituting the value of z and dz, we get that it becomes e iota pi -1 plus r1 e iota theta, the value of z. Then substituting the value of dz, it is iota r1 e iota theta d theta, and denominator will takes the form -1 plus r1 e iota theta into 1 minus -1 plus r1 e iota theta whole square. Substituting the value of z and dz in the given integral. So after making calculations, we get that this r1 and -1 got cancelled, and we can take r1 e iota theta common, and then we can cancel it with the term in the numerator r1 e iota theta, and taking r1 approaches 0 in the next step, we get this integral becomes integral from pi to 0 e iota pi into -1 because r1 approaches 0. This term r1 e iota theta cancelled, so we remain here only the term remains only is iota in the numerator, and in the denominator r1 approaches 0, so -1 plus r1 e iota theta will be converted into -1, and this r1 e iota theta plus 2, when we take this r1 approaches 0, we get only 2. So overall this integral finally converted into minus pi I by 2 and we name it 4. Similarly, in the same way, we can evaluate the integral fz dz over the circular arc CR3, which is also clock in the clockwise direction, and we make the substitutions here because this CR3 is a circle with center at 1 and radius R3. So we make the substitution mod z minus 1 is equal to R3. That is z minus 1 is equal to R3 e iota theta. And from here we can get that z is equal to 1 plus R3 e iota theta. And using this z and dz, we can evaluate this integral 5 and it comes out to be minus pi iota by 2. Now we consider the integral along CR2. Now CR2 is a semicircle with center at 0 and radius R2. So the points on this semicircular arc will look like z is equal to R2 e iota theta because its radius is R2 and center is 0. So we have taken mod z is equal to R2 and then dz becomes R2 iota e iota theta d theta. So now we substitute these terms, that is z is equal to R2 e iota theta and dz is equal to R2 iota e iota theta d theta into this integral over CR2, and when taking R2 approaches 0, this integral comes out to be minus pi I and we name it number 6. Then we have left only with one integral, namely integral C capital R e iota pi z over z 1 minus z square dz, and we can use this integral in the solve this integral using our previous method or using Jordan lemma. So if we use Jordan lemma, then for that we consider the equation of the circle. Since this circle C capital R is a circle with center at 0 and radius capital R, so the substitution for the points on this circular arc will be of the form z is equal to capital R e iota theta, because mod z in this case is capital R, center at 0 and radius capital R. Now if you consider 1 over z 1 minus z square only, then in mod it will less than or equal to 1 by mod z into mod z square minus 1. Here we have used the fact that mod of a minus b is greater than or equal to mod a minus mod b, and therefore 1 over a minus b will be less than or equal to 1 over mod a minus mod b. And also we have used that a minus b mod is same as b minus a. So with the help of these two inequalities, we get that mod of 1 over z 1 minus z square is less than or equal to 1 by mod z into 1 over mod z square minus 1. And now using the substitution that z is r e iota theta, we get that this term is less than or equal to 2 over r cube. And now we come to Jordan lemma. Now in the statement of Jordan lemma, you can see that we have proved that integral e iota az capital Fz dz over some semicircle gamma of radius capital R and center at 0, this integral comes out to be 0 if mod of Fz is less than or equal to m over r raised to power k. And in our case, Fz is 1 over z1 minus z square, and that is less than or equal to 2 over r cube. Therefore, all the requirements of the Jordan lemma are satisfied, and therefore we get, using Jordan lemma, that this integral e iota pi z over z1 minus z square dz over cr is 0 as r approaches infinity. So we name this the answer of this integral to be 7. Now we combine the terms 2, 3, 4, 5, 6, 7, 8, and we use these terms in 1. And when we use all these terms in 1, we get that left hand side of 1 is 0 and right hand side is minus pi I by 2 minus pi I minus pi I by 2 plus integral minus infinity to infinity fx dx. So from here we get that integral minus infinity to infinity fx dx is 2 pi I. So this implies integral minus infinity to infinity fx. Fx was e iota pi x over x1 minus x square. Now e iota pi x is cos pi x plus iota sin pi x. So our integral minus infinity to infinity fx dx becomes integral minus infinity to infinity cos pi x plus iota sin pi x over x1 minus x square dx, and the answer of this integral is 2 pi I. But we have not asked for this integral. In the question, we have to evaluate integral from 0 to infinity sin pi x over x1 minus x square. So for that purpose, we compare the imaginary parts on both the sides. So we get integral minus infinity to infinity sin pi x over x1 minus x square dx is 2 pi. We have compared the imaginary parts. So now notice that integral is from minus infinity to infinity and the integrand is an even function. So this minus infinity to infinity will get converted into 2 times 0 to infinity. So 2 times 0 to infinity sin pi x over x1 minus x square dx is 2 pi, and this implies 0 to infinity sin pi x x1 minus x square is equal to pi, which we want to evaluate. So I hope you understand this. But if you have any problem, then you can discuss with me. At the end of the lecture, I have given you 2 problems to solve. Kindly solve it, send these exercises after solving, and if you have any doubt, you can ask.